We are on the last chapter and we are dealing with probability trees and tables. So essentially, I'm going to try and take you through as many examples as we can. This one is a high school. Half of them are seniors, half of them are juniors. 90% of the seniors take calculus and 70% of the juniors take calculus. And we are going to create a probability tree using all the information that's here. And from that probability tree, I'm going to create a table. And once that table and the trees are both done, then we're going to answer this question. And this idea of creating a probability tree and then making a table is quite common. So I'm doing both. Even although you might not need the table for a specific question, it's good practice to do them anyway. So I'll start off with the first split. In this high school, there is only two kinds of students, seniors and juniors. And half of the school is seniors, so half of them are juniors. So we write everything down in terms of either decimals or fractions. I'm probably going to stick to decimals just because they're easier to deal with in my calculator. Plus, it's easy to compare decimals. It's much harder when they're fractions. Now, what do we know about the seniors? 90% of the seniors take calculus. So 90% is 0.9, and C means you took calculus. Of course, the rest of them are not going to take calculus. So I'm just going to call them not C. What percentage do not take calculus? What percentage of seniors don't take calculus?
0.1.
0.1. Have you noticed the pattern in a probability tree is that any split is made up of two numbers that always add up to 1. So if you know one of them is 0.3, you know the other's 0.7, right? Now, if you do the juniors, it was 70%. So 70% are going to take calculus. And again, then, the not calculus students are the rest, the 30%. So are we comfortable about how the words that are written, you know, like in English, can be transferred into this visual probability tree? Okay. Now, for each one of the 4 end branches, we will calculate the probabilities of these things happening. So for instance, this one here, that's a senior who takes calculus. The chances that you are a senior that takes calculus is 0.5 times 0.9, that is 0.45. A senior who doesn't take calculus is going to be 0.5 times 0.1, and that ends up being 0.05. A junior who takes calculus is 0.5 times 0.7, so that's 0.35. And a junior who doesn't take calculus is 0.5 times 0.3, and that is 0.15. And shouldn't I do a little check at the end? And my little check at the end is, what should all the branches of the tree add up to if you do it correctly? Right, Lauren's saying 1. We agree? 1 it is. And guess what? It is. Now I'm going to create a table to kind of put this information in. There were 2 things that were happening in this story. You were a junior, or you were a senior. And the other thing was you took calculus, or you're not a calculus student. So these numbers here are going to fit in these 4 boxes, right? So these are the probabilities of each of these 4 things happening. So this one here, right, the one my finger is pointing, the top left-hand box, are juniors that take calculus. Which one of these 4 is juniors that take calculus?
0.35.
Agreed. What about seniors that take calculus?
0.45.
Juniors who do not take calculus?
0.15.
And last but not least, seniors who do not take calculus?
0.05.
Are you comfortable how these 4 guys come from here and which one goes where? Does that make sense? Like, let's just take one at random. Let's take that 0.35. That 0.35 is a junior who took calculus. So I go to my table and a junior who takes calculus, boom, right there. Now, these tables should have totals. The row is what you get when you add these two together, and that ends up being 0.8. This row ends up being 0.2. This column ends up being 0.5, and this column ends up being 0.5. And shouldn't they all add up to 1 again as a check that you've added your rows and columns correctly? It's always a good idea to have places to check. So you're going to get a story, and that story is going to give you a probability tree. And that probability tree is then going to create this table. Are we comfortable about from here to here to here? So far, so good. Right. Now you go and read the question, because there might be, 2 questions, or who knows how many. In this case, of just 1. It says, suppose a calculus student is taken at random. What is the probability that they're a junior? Now, since you know that it's a calculus student, we call that a conditional probability. So doesn't the world only belong to that row? So if I'm writing it down, it would be something like this. What's the probability that they're a junior, given that they take calculus, right? That's how you would write that sentence down more mathematically. Right, so what do I know here? Well, I want to know what's the probability that they're a junior. Now, normally these numbers are numbers like 50 and that's 100, right? But you get the same answer by doing the same thing. So the probability then that you're a junior, given that you take calculus, the bottom number is 0.8 and the top number is 0.35. And if it makes you feel better, couldn't I just say 35% over 80, so you've got nice whole numbers, but it's the same calculation. So you just take 0.35 and you divide it by 0.8, and the answer I get is 0.4375. Yeah, let's try using this table to get some more. What's the probability that you take calculus, given that you're a senior? Well, if I tell you you're a senior, doesn't the world now just consist of that column? Right? Now, on the bottom, the total, right? So the green number, right? The bottom goes in the bottom. And what number of these is the calculus one? It's the 0.45. And if you do that, you get nothing 0.9, which exactly actually matches the information that they gave you. So couldn't I do, I don't know, I could do any kind of combination I like. What's the last one? What's the probability that I don't take calculus? Well, if you look at this story, this is not a conditional probability, right? It's just a single probability. So don't I just need to find the two, and it's 2 groups that don't take calculus? Aren't they not calculus, these 2? So wouldn't the answer just be 0.2? So sometimes your answer will just be one of the totals. And sometimes you have to do, a conditional probability. So far, so good. Any questions? Right, you got to think these ones through. They do take. Right. The next one has got too much information for me to write it in English. So I'm going to show you the question with all the written stuff, and then I'm going to just build the probability tree from it. Let's make this. Can I make this bigger or smaller? What happens if I go too much? Okay, that seems to be as good as we got. An airline offers advance purchase fares to customers, and these are tickets that you buy at least 4 weeks before the flight. If you've ever had to take a last-minute flight, trust me, you don't want to. The prices, unless it's a special deal, the prices are through the roof, aren't they? But if you know you're going to be somewhere in 3 months, you probably get a good deal, right? That's essentially what this is saying. So they want to test it out. Well, the airline has noticed that 70% of its customers who buy tickets don't take advantage of the advance purchase fare. And the remaining 30% who do, right? So they have this thing called advance purchase. 70% don't take advantage of it, and the other 30 do, okay? The no-show rate for those who don't take advantage is 45%, while those who do have it, it's only 5%. So we are going to create another person's right. We are going to create a probability tree from all of that information. And sometimes you have to go back and read it 3 times before you figure out what the numbers that you're going to use are. But I'm going to set it up for you, and you just have to trust me on the reading. So they've got a nice little, I don't know if you caught it, but they actually set up the tree diagram for you. So the first thing is going to be no advance purchase. I'm just going to call it that for short. And then you have advance purchase. And then you have the no-shows, people who just don't show up. And then you have the ones that do show up. And you have no-shows, people who just don't turn up for the flight, and those who do show up. So I'm going to go back and read one little piece of that information and start filling in these branches. So the airline noticed that 70% of its customers who get tickets don't take advantage of the advance purchase, right? 70% don't take advantage. Are you happy where that 0.7 came from then? Now, how many do then? What goes here? 0.7 don't use it. How many do use it? Remember, the 2 branches always add up to 1. So what number goes here? Yeah. Actually, they told you that in the story, but they didn't need to. Now, those people who do not have an advance purchase, I'll read on and see what it says about them. The no-show rate for those who do not have an advance purchase is 45%. So if you have that kind of no advance purchase ticket, 45% of them don't turn up. And on this side, can you see why that's 0.55? Right. What about the advance purchase people? Well, for the advance purchase, the no-show rate, who have an advance purchase, the no-show rate is that number. And that must mean that 95% of them do show up. Are you comfortable where I got these decimals if you read through that story with the percentages and no-shows and shows and advance purchase and not advance purchase? Right, once you've got this guy set up, what you've got in question, let's check what that number is again. I think it's 4. It's 3, right? What you've got to do is you've got to write down A, B, C, D, and so on. And they tell you that that guy's A. And they call this guy B. And this guy here, they're calling it C, and so on, right? So that's just their way of getting you to tell them what each of the numbers are, right? So if you're wondering what all the A, B, C's in are, that's what they are. I'm just going to use my thing, and imagine I finished it off. So now I'm going to build the table. I've got a little bit more work to do, but I'm still going to do my table. Let's find out what each of these branches gives us at the end. So no advance purchase and you don't show up is 0.7 times 0.45, and the answer is 0.315. If you want this one, you multiply 0.7 and 0.55, and I get 0.385. If you do this guy times this guy, that's people with an advance purchase and they don't show up. It's 0.3 times 0.05, and that ends up being 0.015. And then lastly, this guy times this guy. So 0.3 times 0.95, we get 0.285. And a quick check, 6. It does add up to 1, so I'm happy. So let's see what our table is going to be. Our table is going to be people who show up and no-shows. And then we're going to people who have advanced purchases and no advanced purchases. So won't these 4 boxes be filled in with these 4 numbers? Okay. What is the probability that it's an advanced purchase show up person? Which one of these 4 decimals is an advanced purchase shows up?
.285.
Let's check it. Advanced purchase shows up. Are we all happy about where she got that from? 285, okay. What advanced purchase no show would be? Wouldn't it be this one here? Advanced purchase no show, right? Advanced purchase no show. That is 0.015. No advanced purchase shows up, 0.385. No advanced purchase and they don't show up, 0.315. So those 4 guys came from these 4 places, just like the last time, right? So now I'm going to fill in with the totals. If you add 285 and this guy to 95, you get 0.4. Sorry, 0.3. Can't count. If you add these 2 together, you get 0.7. Pen's running out of green. Try and find another one. Oh, that's a nice interesting pen. If you add the shows up, that's 5. Oh, too hard. I'm not going to risk it. Not on a Friday. 0.385 added to 0.285, 0.67. And I'm pretty sure that's 0.33. And the whole thing adds up to 1 as a check. Are you comfortable about the totals and how I got this? And that would be the answer to question B. So question A would be basically creating this probability tree with all the numbers that go with it. Part B would be to create this table. Now, once you've got your table, you can then answer any conditional or non-conditional probability. Question C is asking us to find the percentage. Oh, they want a percentage. That's interesting. So the percentage of no-shows. Okay. Aren't all the no-shows these 2 people? Now, if you want the answer as a decimal, it's 0.33. If you want it as a percentage, isn't it 33%? Right, so it doesn't matter what kind of ticket they buy, 33% of the people aren't going to turn up for a flight. That's like 1/3 of the people. Okay. Question D. Give the customers a no-show. So you're told that they're a no-show. What's the probability they did an advance purchase fare? So what's the probability that they had an advance purchase, given that they're a no-show? Only this time they want the answer as a decimal or a fraction. I think it's a decimal. Oh, wait a minute. No, as a fraction. Okay, I can live with fractions. Right, here it goes. Since they are a no-show, doesn't it mean the world only consists of these guys? Great. So the bottom is going to be the total, 0.33. And which one of these two goes on the top? The 0.015 or the 0.315 for advance?
0.015.
Great. Now, if you want that to be a fraction, is it not what calculators are for? So let's find out what that looks like. 0.015 divided by 0.33. And then I'm going to hit math and choice number 1. And isn't it cool that you can do fractions on the TIA? Because I would not want to turn that thing into a fraction. I'd much prefer it was a decimal based on the numbers. But hey, if they wanted it as a percentage, wouldn't I just do 0.015 divided by 0.33 and then times the whole thing by 100 and 4.5% to one decimal place if that's what they wanted. So can't you do decimals if you round them off, percentages if you round them off, or fractions? I mean, any way you like, we can do it. And E is just a sentence, I'll let you do that. Before we leave this question, if this data is accurate, 33% of people don't turn up for a flight. How do airlines cope with that? I don't think it's really 33%. I think realistically it's probably 5%, maybe, something like that. But how do airlines cope with that? Because they do.
Standby flights.
They have standbys, but don't they also overbook? And so if you know, let's say it's 10%. If you know typically 10% of the people who bought a ticket don't turn up, can't you say sell 10% more tickets than there are seats? And 9 times out of 10, everything's fine. Don't you actually? You're not flying with empty seats because the people didn't turn up, right? But I've been in flights, a flight of reasonable, or used to fly a reasonable amount of time. Has anybody ever had the thing where it was overbooked? Where actually, more people, they did turn up. What did they do with you, Lauren? Or what happened? Maybe not to you personally, but what did the airline companies do when they're overbooked?
They offered standby flights for people that didn't have seats, or vice versa. They were supposed to be overbooked, and then we had a bunch of standbys. I flew military a lot, so
God, you get bumped a lot, yeah.
Yes.
Yeah. I'm in a different situation from you because in your case it's hard luck, get the next flight, kind of, right? Is that kind of how it works? Yeah. If you're a paying passenger, what they can do, and it's kind of cool, and I've done it once, I've accepted it once, is that they let you get a later flight. That's right. Okay, this one's booked, but there's another one in 2 hours. Get that one. And they give you money. And they tend to give you money in the form of a credit. I got I think it was a $200 credit once. I was flying back from my conference and it was overbooked. And I didn't mind waiting, went and had a meal. It wasn't a big deal. And I got a $200 freight credit. So anybody done better than that? Because I've got a story I want to tell you about another student. Anybody done better than getting $200?
technically got a free flight once.
Right, that's cool. Yeah, I got a student who get bumped up to first class. It was, well, I guess the flight wasn't fully booked, but in the area that he was sitting, it was fully booked. And they just bumped him up to first class, so he got to fly back first class. That's pretty cool, isn't it? That's never happened to me. Okay, let's move on. And hopefully you're getting a feel for this. There are only 5 questions, so you know that there's not a lot of difference happening so far, at least in the 2 that we've done. So let's do our second last question, question 4. I'm not going to jump back and forward. I'm just going to read the story out and then create the tree from it. Consider randomly drawing 2 students without replacement. So that's going to be a little bit different, without replacement. So I'll put that in right now. Right. And it's got a class with 50 students. And these 50 students, 5 are left-handed, so that means the 45 are right-handed, right? The predominant hand. And they are wanting us to create a probability tree, right? To do with selecting left-handed and, well, that's annoying. They're calling them not left-handed. Can I just call them right-handed because it's easier in my brain, right? So left-handed and right-handed. And they're picking 2 students. So let's see what that probability tree would look like. Right, you pick your first student. I'll put a 1 there just to represent first student. And the first student could be left-handed or right-handed. No biggie there. The probability that you are left-handed now, isn't there 5 out of 50 students who are left-handed? So 5 out of 50. What's the probability the first student's going to be right-handed?
45 out of 50.
Agreed. Are you happy about the 2 things add up to 1 again, right? Just with fractions. Now here's the funny part. Here's the bit you have to be a kind of aware of. Second student is now going to be picked. They could be left-handed, they could be right-handed. But things are going to get a little bit uglier now. If you travel this pathway, wasn't the first student left-handed? So at this point in the world, aren't there 49 students? But of those 49 students, only 4 are left-handed, and the other 45 out of the 49 are right-handed. Are you happy about how it's 4 out of 49 and 45 out of 49 for this branch? Does that make sense? A left-handed student get used up. Now there's only 4 out of 49 left, and there's still 45 out of 49 right. Now let's go the other branch. The first person was right-handed. So isn't that only 49 students to pick from, right? He's picked. And of those 49, aren't 5 of those 49 left-handed? Okay, how many of the 49 are right-handed?
$44.
Agreed. See, if you know that number, can't you just figure that number out? Because it's always what's left in 1, right? So if that's 5 out of 49, how many are left? Oh, 44 are left. If this is 1 out of 50, wouldn't that be 49 out of 50, right? It's always the 2 together give you 1, right? You either are or you're not, whatever the thing is they're counting. Now, in this particular combination, we are going to create the table and do all the other things because I want practice at doing that. And I'll try and use this pen, but it's a bit thick. 4 different events. So 4 out of 50 times 4 out of 49. 5 out of 50 times 45 out of 49. 45 out of 50 times 5 out of 49. And lastly, 45 out of 50 times 44 out of 49. And I'm just having a quick check. Do they want decimals or not? No, they want fractions. So I'm glad I did it that way. If you multiply these two together, you're basically going to get 5 times 4 is 20 on the top, and 50 times 49 is going to be 2450 on the bottom. And now I'm going to go 20 divided by 2450, which is that guy. I'm going to go math number 1, and it's 2 over 245. Well, you just trust me that the calculator figured it out. Right. In this next one, actually, if I wanted to, couldn't I just do that as a decimal and turn it right into a fraction? I think that's a little bit quicker. So here goes. Put brackets around things. It's always safer. So I'm going to do 5 out of 50, bracket, 5 divided by 50, close brackets, times another bracket, 45 out of 49. Ugly decimal, math button number 1, ugly decimal, becomes 9/98. Next one. I know the answer to that. And last one then. 45 out of 50 times another bracket, 44 out of 49. Ugly decimal, turn me into a fraction. 198 out of 245. Can I just pretend that that adds up to 1? Because I just don't want to do it. It would take too long. So far, so good. Right. So the major difference between this one and the others, weren't the other ones, they told you some of these numbers and they're all decimals, but in this one, you had to do the, without replacement thing, and you had to calculate how many people were left-handed out of what total. So I'm now going to create our table. And no particular order. I guess I should try it the order that they've got. Do they have an order? Oh. That's all you need to do. That answer's called A, that's called B, C, D, E, F, G, H, I, J. Okay. I want to do it anyway, because you don't get a lot of practice. So how about left-handed and right-handed? What else could you do with this? Oh, I guess you could do first student, second student. So a left-handed student who is first and yeah, I guess you're right. Yeah. I don't think that table would make much sense anyway, so I guess they were right not to ask. Oh, we have got our last question. And it doesn't even have a probability tree in it. And this is going to be interesting. The following table shows the disease status and the test status for a population of patients who are tested for the disease. God, that's nice and vague. Can we just pretend it's COVID? Because that's relative, right? So what we have here is that 53 represents 53 people who have the disease and tested positive. And wouldn't this 6 represent 6 people who had COVID, but they tested negative? And in case you're wondering, well, that doesn't seem real. You know that every test that you can ever make has a failure rate. In other words, you don't catch everybody. Now, there are lots of reasons for it. Couldn't it be that the person has virtually just caught it 2 minutes ago? And so the antibodies, whatever it is, aren't really that big and they're not in their system and you can miss them, right? It could be that the test's not that good, you know, that the test only finds it when it's really obvious, kind of thing. Whatever reason, it's here. In this case, 55, no disease, and 386 negative. You would expect that. Wouldn't you expect a test to catch people correctly a lot more than they get it wrong, and to test positive when there was nothing wrong with you, right? Quite a small. Is the distribution of those numbers reasonably sensible, right? Does anybody know what you call this mistake, where you had the disease, but the test says negative?
False negative.
It's called a false negative. And up here, not surprisingly, that's called a false positive. If you're a manufacturer of a test for COVID or for anything, which one of those two tests would you prefer to be as small as possible? The false positives or the false negatives?
False negative?
Correct. Isn't the false negative you telling somebody they're okay when they've got the disease? Isn't that a more serious mistake? Right. So not all mistakes are equally bad. Okay, what about a false positive? Well, you don't have the disease, right? That's the bottom line. You've tested positive for it. What could go wrong there? You'll get worried for a little while until they recheck you and say, oh, sorry about that, we were wrong, you're okay. Right? That's the consequence of a false positive, right? A little bit of worry, but you know, it's not going to kill you, right? In a different world, couldn't a false negative kill you? You think you're okay, so you're not going to get treated, right? Nobody thinks you're ill. And then, you know, the symptoms suddenly appear during the night and, you know, boom, you could be dead.
I'd like to challenge that.
Go for it.
With a false positive, when you have to go out and tell everybody you've been in contact with, that you may have caused them to get COVID, you might get killed anyway.
Well, I never thought of that, but I would hope that the public would be a little bit more generous than that, I guess. Okay, so let's look at this table and see what kind of, how we can use this table to answer some questions. So the first question is the prevalence of the disease as a percent. Okay, so if you look at this, would you say, oh, by the way, this is 500 people. So they checked 500 people to get this data. Would you agree that there's only 59 have the disease out of totally 500? So if you want to find that as a percentage, you take the total number who have the disease, which is 59, out of the total number in your sample, which is 500, and you make that a percentage. So 59 divided by 500 is 11.8%. And we're comfortable where that number came from. Okay. Now, the next word they use is proportion. In the language that they use, what can a proportion be? Is 82% a proportion? No. So what are they asking for?
Fraction or decimal.
A fraction or a decimal. Since there's no mention of decimal places in this question, it either means the fraction is a really nice fraction, right? Okay. And so I would suspect they mean a fraction, right? In question C, do you see they say 84 decimal places? So in that case, I'm assuming that this is a fraction and that is a decimal. And the reason I'm doing that is, can WebAssign sometimes be really annoying, where you give the right answer, but not the way you wanted it to be, right? So you gave the answer as 0.12 and it wanted to know it was 3/50 or something, right? That kind of issue. So back to the question then, the proportion of the population that has a positive test. Well, the people who have a positive test were 108. So this was going to be oops, if I can click this in, 108 divided by 500. And allegedly, that's going to come out as a nice fraction. So although you can't see me hitting it, I'm doing it on the calculator, and it's 27 125s. We comfortable with that, guy? Okay, next one. The sensitivity of the test. Round your answer to 4 decimal places. So I guess I need to know what the sensitivity is. I think I know what it means, but I don't know that term exactly the way they mean it. The sensitivity of the test in my mind is what percentage of the time do they get it right? Does that seem reasonable? So you said you had the disease and you did. They said you didn't have the disease and you didn't, right? That's that. So bearing in mind, that's what I believe they mean by the sensitivity of test. I'm going to say, look, those 53, didn't the test get it right? And did it not 386 people, didn't the test predict it correctly as well? So I'm adding those two guys together. And so 53 correct, they add another 386 correct. So they got it correct in total 439 times out of 500. And so I'm going to go 439 divided by 500. And I get, well, I'm a bit worried about my answer, but never mind. 0.878. Okay. Oh, that's interesting. I do not know what this book means with that now that I've seen this one. Has somebody got this guy handy? Oh, wait a minute, maybe I can do it. Let's put in the key. And that way I'll figure out. I know what the last two are. Well, I can see what they are. And it's not my number. So these guys here come from this table. And this guy, oh, did they change the table? You've got to be careful to change the numbers when you do that sometimes. Is that the same numbers I had originally?
Yes.
Okay, so that's good. So all I need to do is figure out where 0.8983 came from. So the sensitivity of the test is not getting it correct. I wonder if it means getting a positive correct. Let me check that. 53 divided by 59. You know what I would be doing if I had the time? Wouldn't I be going to look at the ebook, and the ebook would say sensitivity of a test is this, and then I'd know what they were meaning. But since I don't have that, we have got it. The sensitivity of the test is the percentage of the time they positively identify the test. So they got it right 53 times out of 59. So that guy is how many times you tested it and you got it right for the test. Now this guy here, I'm assuming, is how many times you got it right when you told people they didn't have the disease. So that should be 386 people out of 441 that were tested. Check that fella. 386 divided by 441. And I am correct. Okay, now I know what they mean by that. The sensitivity of the test is what percentage of the time does the test correctly identify that you have the disease. And the specificity of the test is what percentage of the time does the test correctly identify that you do not have the disease? Okay. Although I kind of liked my answer. Wouldn't my answer of getting it, how many times you got it right, also be a good number to know? But it's not the numbers they're asking for unless it's the last question. The predictive positive value of the test and the predictive negative value of the test. Oh, I saved myself by the bell. We are finished. So you are going to find out by going to the ebook and finding out what the predictive positive value of the test is and what the predictive negative value of the test is. I'm pretty sure that it's something to do with 53 out of 108, right? And 386 out of 392. I'm pretty sure it's those guys, right? But you can double